The first scientific step came with John Dalton in the early 1800s. Dalton proposed that matter is composed of small, indivisible particles that combine in fixed ratios. His atoms were simple spheres, essential for chemistry but lacking detail about internal structure. His theory set the stage for discoveries to come. In 1897, J.J. Thomson discovered the electron while studying cathode rays. This proved atoms were divisible, containing smaller, negatively charged components. Thomson imagined the atom as a sphere of positive charge with electrons embedded inside, his plum pudding model. It was an important advancement but incomplete. Then came Ernest Rutherford. By firing alpha particles at thin gold foil, he expected them to pass almost straight through. Instead, some deflected sharply backward. This shocking result showed that most of the atom is empty space, with almost all its mass concentrated in a tiny, dense, positively charged nucleus. This nuclear model revolutionized physics, yet it posed a serious problem. If electrons orbited the nucleus like planets, they should radiate energy and spiral inward. Clearly, something deeper was at play. In 1913, Niels Bohr offered a solution by blending Rutherford's atom with early quantum concepts. He proposed that electrons exist in fixed energy levels, stable orbits where they do not lose energy. They can only jump between these levels by absorbing or emitting light of specific energies. Bohr's model explained why atoms are stable and why hydrogen emits light in distinct colors. Though later replaced by more advanced theories, it served as a crucial bridge between classical physics and quantum mechanics. Early 20th century experiments revealed something astonishing. Light behaves as both a wave and a particle. It can create interference patterns like waves, yet also strike metal surfaces as individual particles, photons. Soon, scientists discovered that matter behaves the same way. Electrons can act like waves under certain conditions. This dual nature defies classical reasoning and forces us to rethink what particles even are. Werner Heisenberg deepened the mystery with his uncertainty principle, showing that position and momentum cannot be measured precisely at the same time. This is not a limitation of our instruments. It is a fundamental property of nature. At the quantum level, particles simply do not possess perfect simultaneous values for these properties. Then, Erwin Schrödinger introduced his wave equation, describing particles as wave functions, mathematical expressions representing probabilities. Electrons are no longer tiny marbles orbiting a nucleus, but clouds of potential locations shaped by allowed energy states. Thus was born quantum mechanics, a new framework revealing a universe far stranger than previously imagined. As quantum theory evolved, scientists realized that particles are not truly fundamental. Instead, the universe is filled with underlying fields, and what we call particles are simply vibrations or excitations of these fields. Electrons are ripples in the electron field. Photons are ripples in the electromagnetic field. Quarks appear from the strong nuclear field. This perspective is the heart of quantum field theory, QFT, which unifies particles and forces in a single elegant framework. Perhaps the most surprising idea is that the vacuum, what we think of as empty space, is actually bursting with activity. Quantum fields can never be completely still. Virtual particles appear and vanish, tiny fluctuations ripple constantly, and this restless energy affects the forces and structures around us. Nothingness, at the quantum level, is full of motion. In QFT, forces are transmitted through messenger particles. Photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. These interactions form the Standard Model, our most successful theory of the fundamental universe. Yet gravity, dark energy, and dark matter remain outside this model, pointing toward even deeper physics still waiting to be discovered. Quantum effects, surprisingly, do not remain confined to subatomic particles. Evidence suggests that living systems may use quantum behaviors to function more efficiently. Photosynthesis may use quantum coherence to move energy rapidly. Birds might navigate using entangled particles in their vision systems. Enzymes may use quantum tunneling to accelerate biochemical reactions. This emerging field, known as quantum biology, suggests that life has evolved in ways that exploit quantum processes. Perhaps the most puzzling quantum phenomenon is entanglement. Two particles can become linked so that a change to one instantly influences the other, even when they are separated by great distances. Einstein called it spooky action at a distance, yet it is now harnessed in quantum computers and secure communication systems. Entanglement reveals a universe where deep connections exist beneath the surface, transcending traditional boundaries of space and time. The deeper we explore the quantum realm, the stranger and more fascinating the universe becomes. Particles blur into clouds of probability. Empty space teems with energy. Fields ripple to create matter. Biological systems may rely on quantum behavior, and entanglement ties distant objects together with invisible threads. These discoveries raise profound questions. What is truly fundamental, particles, fields, or something deeper? How does consciousness fit into the fabric of the quantum world? What lies beyond the standard model? Could entanglement extend across the entire universe? The quantum realm is not just a scientific concept, it is a profound glimpse into the underlying structure of existence. It challenges our understanding, stretches our imagination, and reminds us that reality is far more mysterious and intricate than it appears on the surface.